Sometimes in mathematics, the most beautiful results are hidden behind expressions that look almost intimidating at the first glance. Today's problem is one such classic. We are asked to evaluate a finite sum involving cot² x at very specific angles. The angles that seem carefully chosen, almost like pieces of a large puzzle. And surprisingly, this complicated looking sum collapses into a clean, elegant formula. As you can see, it is present in the right hand side of the equation what we have to prove. But that's not the end of the story, you can see. Further, what is hidden inside this finite identity is something much deeper. A bridge to an infinite result. From here, we will uncover one of the most famous series in mathematics, that is the summation k goes from 1 to infinity, 1 by k square, how it appears to be pi square by 6. So today we are not just solving a problem, we are witnessing how finite patterns reveal infinite truths. Let's dive in. So the calculation is going to be very lengthy, so we have to have patience. So the idea is we have to start from the complex number. How we can start? We know that suppose I'm writing the cosine theta plus I sine theta to the power n. That is going to be by using the de Moivre's theorem, that is cosine n theta plus I sine n theta. On the left hand side, since I have to involve the cot, I'm going to do this thing. Let's take the sine common from this binomial expansion what we see in the left hand side. Where is the binomial expansion we can see? Here. You can see here. This is the binomial expansion. So I'm taking the cosine, not cosine, sine theta common. So we get sine to the power n theta out. And we are left with the cot theta plus iota to the power n. And on the right hand side, we again have cosine n theta plus I sine n theta. Now we expand this second term on the left hand side by using the binomial expansion. And what we get is sine to the power n theta. And here I have the expansion. The first term will be cot to the power n theta, then nc1 cot to the power n minus 1 theta iota plus nc2 cot to the power n minus 2 iota squared, and so on. I'm not writing all the terms. So this will give you cos n theta plus I sine n theta on the right hand side. Now my intention is to equate the imaginary terms from both hand sides. You can notice that from this expression, I'm going to collect all the, let's call this as 1. And from this expression E, I'm going to collect all the terms containing imaginary terms. So imaginary terms, it means I want to say that I have to find imaginary part of this E. So how do you find the imaginary part of E? It's not difficult. We just take all the terms containing I. It means the first term will be have nc1 cot to the power n minus 1 theta. Then the second term, you notice it will come when I have the power of I is 3, because I cube will give you negative I, and that will I get when I have nc3. So nc3 and the cot to the power n minus 3 will be there. The next term, which has the power I to the power 5. So of course, I will get the power 5 for I, and that will give the imaginary part. So NC5 I will get here, and that is cot to the power n minus 5. Similarly, I get the next term NC7 and cot to the power n minus 7 and so on. So I'm not going to write all those terms because it's not necessary. Now what I'm going to do, in equation number 1, what we have assumed here, in this equation I'm going to compare the imaginary parts from both sides. So on comparing the imaginary parts, from both sides from 1. So what we get is, on the left hand side, what we have, sine to the power n theta into the imaginary part of the E what we just found, and that must be equal to sine n theta. Now this imaginary part of E is a very important term here. On that only we have to work everything. There I missed this theta there here, but I think there's no such problem. Okay, so you notice what is happening. I have to have the cot square theta here, but I only got the cot theta in every term in the expansion of imaginary part of E basically. Let me write this first. So sine to the power n theta here, and we will write slowly. This is going to be NC1 and cot to the power n minus 1 theta minus NC3 cot to the power n minus 3 theta plus NC5 cot to the power n minus 5 theta, and so on. I'll stop here. On the right hand side I have sine to the power n theta. Now to make this cot square in the scene, to make this cot square appear in the scene, what I'm going to do is I'm substituting n is equal to 2m plus 1. So let's take here n is equal to 2m plus 1 first. When you do that, what will happen? What is the consequence of it? Let's try to understand. This left hand side I will have sine to the power 2m plus 1 theta, but you notice this will become 2m plus 1 c1 and cot to the power 2m theta. The next term I have 2m plus 1 c3 and cot to the power 2m, and you are substituting here 2m plus 1, so it will become 2m minus 2 theta, and again 2m plus 1 c5 cot to the power 2m minus 4 theta, and so on. On the right hand side as well, the sine will become with the angle 2m plus 1 theta. Now observe this thing very carefully. The left hand side, now I can see this is sine to the power 2m plus 1 theta as it is, no problem. But this bracket is telling something wonderful story here. 2m plus 1 c1, and this is going to be cot square theta to the power m. The next term I can write 2m plus 1 c3 cot square to the power m minus 1, and 2m plus 1 c5 cot square theta to the power m minus 2. I think you understood the story. And this is sine to the power, sorry, not sine to the power, sine 2m plus 1 theta. So we actually made the cot square happen here. Like we made this appear, this cot square theta. Now we have to work on how do we get the cot square k pi by 2m plus 1 appear. So for that, let's consider this thing. What we consider here is this one. From here to here, we just assume everything as the polynomial of x. Why it is so? Let's try. So what I'm saying that the P of x is nothing but 2m plus 1 c1 x to the power m minus, and since the polynomial of x and the degree is m, so I can write the m as a subscript here so that it will indicate that the degree of this polynomial is m. Now here 2m plus 1 c3, and I can write x to the power m minus 1, then 2m plus 1 c5 and x to the power m minus 2, and so on. You can notice this cot² theta we have substituted there to get this value. It means, I mean to say that Pm cot² theta, when we substitute, we get this term here. That is going to be this one. So what we can write now, this entire equation as is sine to the power 2m plus 1 theta is equal to Pm, not a is equal to, sorry, that is going to be into Pm cot² theta, that is equal to sine to the power 2m plus 1 theta. Now we have almost got this cot² theta with this thing, what we need here. But now how do we find the sum, and what is the meaning of this sum basically in the left hand side? This k goes from 1 to m, so what does it mean? We will reveal it. This is the equation we have, and let's try to understand. Also notice one thing, that the angle I need here k pi by 2m plus 1. You notice it is actually here, there is a hint. Why it is k pi 2m plus 1? If this equation happens to be correct, and this is valid for some particular theta, it should satisfy both sides. And let's see how. So what is the meaning of this? Is a sine of 2m plus 1 theta I am setting to 0. If I set to 0, this left hand side, the right hand side by the way, 0, what will happen is the 2m plus 1 theta is going to be k pi, where k belongs to integer. By the way, this expansion or de Moivre's theorem we apply here in the very first step in the beginning, that is actually true for theta belongs to 0 to pi by 2. So theta belongs to 0 to pi by 2, this is actually we have taken, and here k belongs to integer. It means it is all the integers we get the multiple of pi, and so this will become 0. Is the particular, and notice what is happening, the theta will become here k pi by 2m plus 1. Now notice one thing, it means that when we are substituting theta is equal to k pi by 2m plus 1, the right hand side and the left hand side becomes 0. What does it mean? It means that since sine theta at any number 0 to pi by 2 is not going to be 0, so this is not going to be 0 at k pi by 2m plus 1, this term should be 0 to make this valid at theta is equal to k pi by 2m plus 1. What I mean is that this equation 1 holds true at theta is equal to k pi by 2m plus 1 if Pm cot² k pi by 2m plus 1 is equal to 0. Why so? Because sine theta is not equal to 0 at any this value. It means what? That we got here this polynomial, what we found in terms of the cot² theta, that sum should be 0, means that value should be 0. What is the meaning? It means that 2m c plus 1 c1 and x is going to be what? x is going to be the x is a placeholder of the cot square k pi by 2m plus 1. Now notice one thing, this k is actually the integer value, and when we are substituting, let me just do in this way only. This is going to be pm, and we are substituting cot square k pi by 2m plus 1 is going to be 0. And notice what is happening here is the k starts from 1 to m. So let me copy this thing from here, and let's analyze this thing, what they're asking carefully. So notice one thing here, the k starts from 1 to m. So when we take k is equal to 1, the first value we get, or 2 again the second value, it means that all these values what we are substituting there in the polynomial, they are indicating the sum of roots, because the degree of the polynomial is m only. So let me clarify this thing. The polynomial what we have is here. Let me just copy. So this is the polynomial we have, and in this we are substituting these values. So for k is equal to 1 we substitute something else, for k is equal to 2 we substitute something else, and since this pm x is what, not pmx, pm cot square theta, we can write pm plus 1 c1 cot square theta to the power m minus 2m plus 1 c3 and cot square theta to the power m minus 1, and so on. Now notice when we substituted theta there, substitute k is equal to 1, and then the first theta you are substituting pi by 2m plus 1. At that particular theta, the left hand side and right hand side becomes 0. It means that theta along with the cot square theta, so to speak, it means the first root we got that cot square pi by 2m plus 1. The second root we get if I have cot square 2 pi by 2m plus 1. It means if they're asking this thing, they are taking all those roots and they're finding the sum of roots. So the meaning is that because they have not exhausted, I mean, they not excluded anything, k is equal to 1 to m. So they're taking full all the values which can be the possible roots of this equation. It means the summation k is equal to 1 to m cot square k pi by 2m plus 1 is nothing but sum of roots of the equation what? Of equation, let's say equation 2 here, this equation, or maybe this equation, doesn't matter, equation 2. So sum of roots you know how to find. Sum of roots will be the negative of the second coefficient by the first coefficient. So we get here 2m plus 1 c3 divided by 2m plus 1 c1. Let's calculate it. So it will give you 2m plus 1 c3 divided by 2m plus 1. Now we simplify further, so that will give you 2m plus 1 factorial and divided by 2m plus 1 minus 3, that is minus 2 factorial, and divided by 2m plus 1, and also there is 1 3 factorial. So what we get now is 2m plus 1, then 2m, then 2m minus 1 as well, and 2m minus 2 factorial will go away, and here I have 2m plus 1, and then 3 to the 6. Here 2m plus 1 cancels, and 2 will also cancel this 6. So we get m into 2m minus 1 by 3. So this was the hidden actually charm of this calculation, that how we can start with this complex number and we end up with this proof. Once we get this proof, how do we prove the second part of this question? K is equal to 1 to m cot square k pi by 2m plus 1 is equal to m times 2m minus 1 by 3. We have proved this thing. The second part of the question is, I have to prove this relation, that 1 by k square is a infinite actually. So this, you notice, this for the finite value, k goes from 1 to m. But now with the help of this finite sum, we are going to prove the infinite sum. How do we prove it? Let's see. This I have to prove. Now this cot square is actually a little bit helpful. And how do we, so to prove this thing, we need actually limit concept. And particularly in limit concept, we need the sandwich theorem. How do we apply the sandwich theorem? So we start from the basic one and then we build up. So you know that the sin x is lesser than x, lesser than tan x, or any, let me just write x belongs to 0 to pi by 2. I'm actually considering from the beginning the same thing. Now, what is going to happen here? That thing is, let's square it, because I need there, or let's first reciprocal, I think, because cot square theta I need. Okay, let's do it reciprocal. So for reciprocal, what we get here is 1 by tan squared x, that is cot square x, and 1 by x, y, and square also, because I need cot square. Okay, and cosec square x. I hope I'm correct. So cot square x, I just write cot square x, no problem, because I'm going to substitute this angle there, you notice, and here 1 by x square, and this I can write 1 plus cot square again. So note what will happen if I substitute this angle, there is no such problem. And automatically the k will come there, what is needed there. So let's see, I'm substituting in this inequality x equals to k pi by 2m plus 1. So what we get it here is cot square k pi by 2m plus 1. Here, if I substitute this thing, the 2m plus 1, the whole square will go on the top, and pi square also become in the denominator, but here will become 1 by k square. Here again 1 plus cot square and k pi by 2m plus 1. Now I'm going to apply the summation. K goes from 1 to m first. So if you apply there summation, k goes from 1 to m, cot square k pi by 2m plus 1, and then again summation, k goes from 1 to m, and this constant, because k is here only, so this can be treated as a constant, this term I'm talking about, because it is independent of k, so I can keep it aside. So 2m plus 1 whole square by pi square, and summation k goes from 1 to m, 1 by k square, and this is again summation k goes from 1 to m, 1 plus cot square k pi by 2m plus 1. Now notice one more thing. This value we have already found in both sides. This right hand side also we can substitute this thing, and also we can substitute this thing. So what is this value we already found? M times 2m minus 1 by 3. So let's substitute it. So we get it here, m times 2m minus 1 by 3, and this is, I can expand it, so we get 4m square This is going to be 4m square plus 4m plus 1 divided by pi square. And notice this is our key term, what we have to evaluate, a square. And this is going to be m. And again, I can write this as m into 2m minus 1 by 3. Now you know what to do now, because since we are actually working on the infinite sum of this, I can apply the limit m approaches infinity, both sides. So let's apply it. Limit m approaches infinity. So this is going to be, before that, I need to have this thing alone actually. So what I should do, I can divide the entire equation, the entire inequality with this term. So we get it here, pi square by 3 times, this is going to be 2m square minus m divided by 4m square plus 4m plus 1. And this is the same thing what I have to find it out. And this is going to be 3m, the 2m square. So this will give me 2m square plus m by, again, same thing here. So 4m square plus 4m plus 1. And this 3 was already there. So it will become pi square by 3. Now we do the same thing, what I told, limit m tends to infinity. This guy, pi square by 3 and 2m square minus m by 4m square plus 4m plus 1. And this goes, when infinity you take, this automatically k goes from 1 to infinity, 1 by k square. And by the way, you take the limit, so we apply the inequality sign also, m tends to infinity. And we have 2m square plus m by 4m square plus 4m plus 1. You already know the answer we already achieved. So we know that this limit, particularly when m tends to infinity, is going to be 1/2. So this left hand side, this limit approaches to pi square by 6. This right hand side, this limit is also approaching towards pi square by 6. And so we proved that the summation k goes from 1 to infinity, 1 by k square, is pi square by 6. Alright, I hope you enjoyed this calculation. It's lengthy, but it's satisfactory, and we understood everything. We started from complex number. We intermediate step, we got the polynomial concept, and we end up with the limit, and before that it was summation. So this kind of questions are satisfactory if you are a math enthusiast and you love to do the questions like this. See you in the next video with some other such interesting questions. Till then, stay math active.